About calorie restriction. Okay, so the definition of calorie restriction is you have to reduce calorie intake and you have to have an adequate intake of nutrients so that you are not deficient in vitamins and nutrients so that you don't end up with deficiency diseases. The lifespan is about linearly correlated with the percent of restriction that is being done. This is data from rodents. And it's also linearly correlated with the age of start. So the earlier you start, at least in rodents, this data is again, the better the increase in lifespan is. And then Speckman has done some calculations. Now, if you just assume that you can just take the rodent data and you can put those data on humans, and of course that's a lot of speculation, but it's just to illustrate the extreme effect of the age at which the diet is started. Then when you start at age 23, you get 9 years and 5 months, so it's about 10 years extra of life. While if you start at 48 years, you get 2.8 years, that's still reasonable good. But when you start just 7 years later, it's only 6 weeks anymore. So it seems from animal data that a CR diet works best when started quite early. CR has been tested, it's the oldest life extension intervention. It was actually, the first study was before 1900 in spiders, 1895 or 85 or something like that was the first study with spiders. And since then it has been tested in quite a lot of organisms, from even bacteria and unicellular organisms to, of course, very well-known model organisms such as C. elegans in aging research and Drosophila, but also, of course, in rodents, even in dogs and well, in cows, but that's not really a good study on CR because they just looked at what happened during the winter months when the cows were eating a bit of less calorie-dense diet than normal. More recently, in monkeys, there are some interesting studies that I will look at, but then there are also studies that fail to show a lifespan extension, including in wild mice, in another nematode worm, in the common housefly, in the medfly, in a kind of spider, in a kind of butterfly, and in some species of the water striders and the rotifers. In Drosophila I put that in yellow because there are contradictory studies, and it's extremely difficult to do calorie restriction in Drosophila because you really can't measure how much every individual fly is eating, and there are some discussions about compensatory feeding and so on, but I won't go into details. So more recently, the influence of genetic backgrounds has been studied. So in this study by Layo et al. In 2010, they looked at 42 strains of this panel. That's a panel of inbred mice, so they with genetic variation. So they took a few mice strains and they combined them and made these different strains from them. And then they put them on caloric restriction and they looked at them and they saw, well, when you looked at ad libitum, you have a huge variation in lifespan. So that seems to be, you have quite a bit of genetic variation when it comes to the aging pathways or the aging genes. So then when you put those on caloric restriction, you see that some have an increase in lifespan and some have a decrease in lifespan. And the data are presented here for two of the panels, for the males and the females of this strain. This panel of strains, because every bar represents a strain. And so what the bars are essentially is the calorie restriction, the lifespan on caloric restriction, proportional to the lifespan with non-calorie restriction. So when the bar is above the axis, it means that the calorie restriction lengthens the lifespan, it's higher, and when it's below, it means it's reduced. So you can clearly see that calorie restriction increases lifespan in these and decreases in these. Now it's significant for only 2 strains here, and for 8 strains over there in this panel, positive. And a decrease for 10 here and 11 there. That is significant. The study was also repeated with only female strains, 42 of them, of which 27 were common, because there are many more of these strains than the ones that they tested. I think at least 95 or so different strains have been developed. And so they took another 42 strains, of which 27 were in common with the first study, but they only used females, and again they found an increase is significant in 9, but a decrease that was significant in lifespan on CR in 8. Okay, so then there was earlier this year a meta-review published. So the medium lifespan in half of all published study experiments. Now, this is the half of the studies that are the most positive ones, right? And there you have in rats between 15 and 45% increase, and in mice you have from 4 to 27%. As you can see from in the mice, 4% that's not much. That's because the other 50% are worse off. So again, it seems this meta-review is suggesting that the effect of CR is not as solid as it was assumed to be in the past. But in general, it's still a little bit more positive than negative. There are still more studies showing a lifespan extension and more animal strains showing a lifespan extension than those who had a decrease. Now in primates, there are very recently, from 2009 and from this year, 2 big studies that have published their results, and they are opposite results. But there are more studies in primates, they are all listed here, and I will quickly look at some others. The Baltimore study, these are the most recent data I could find on the survival, so it's from 2003. And they found an increase in survival here. So the study here is not ended yet. It still runs through, and there are no more recent data on the mortality. Then you have the Mount Sinai School of Medicine study. They have no published data on a lifespan, but they do have a lot of data on specific biomarkers, and I'm not going to discuss them here, but it's sufficient to say that they look to be healthy, that CR seems to improve health in this. Okay, then we come to the Wisconsin study. That's the study published in 2009 in Science that showed a positive effect from calorie restriction. However, they had to remove the animals that died from non-aging related causes. That included animals who were injured, who died during procedures. For example, they were sedated and then they didn't wake up anymore, and that was considered non-aging related. If you looked at the total mortality without correlation, then lifespan had no difference. So, well, that's what you can see here, overall mortality versus age-related mortality. Also, when you look at the diseases, you can essentially see that the calorie-restricted animals are doing much better, especially here in glucoregulatory impairment. So the calorie-restricted animals had not a single case of type 2 diabetes. This NIA studies a bit different results, essentially boiled on that they didn't observe a significant increase in lifespan. And when you look at the disease profile, it's not looking very good either. There is essentially virtually no difference. In diabetes, you could say there is some protection against it, but for the other diseases, there is virtually no difference. In fact, the CR group had essentially even abnormal levels of fasting blood sugar and also of triglycerides, which is quite normal because most studies in general on CR really, and even in human studies, show that CR decreases blood glucose and decreases triglycerides. That was one of the problems I had with the study that was quite abnormal and really deserves an explanation, which there isn't at the moment. So what could be the reason for the difference? Well, nobody knows, but we can just speculate on the different options. The diet was, of course, different. The science study used much more protein, much more fat than the nature study, and also the diet was made up much more of sugar, pure sugar, than of starch, which in our common wisdom would suggest that the science diet was essentially less healthy than the nature study. Yet it seems that the science study had positive results and the nature study had negative results, so it's a bit hard to explain this. One reason really might be, I think, that the 5% fat is a bit too low. You really might need some more fat in a diet. The protein level was a little bit different. It was higher in the nature study. Now, protein in humans, from Fontana's study, we know that you have to reduce protein intake to reduce IGF-1, and IGF-1 is one of the possible mechanisms by which CR might work. In rodents, that's not the case. In rodents, IGF-1 is reduced independent of how much protein there is in the CR diet. So we could speculate that monkeys are more similar to humans than they are to mice, and so that they might have the same, that reduction in protein intake is needed. But this is purely speculation, and again, the difference in the protein intake in the diet is not that huge either. The control monkeys in the nature study were slightly restricted, so they were, in a sense, made healthier than in the science study. The nature study had a bigger genetic diversity, which again, as we saw with the mice models, CR might really be dependent on the genotype of the animals being studied. There are in the nature study no data yet on the maximum lifespan from the young animals. However, it's highly unlikely the authors conclude that there will be any significant increase in maximum lifespan, given that there is so far no significant difference at all between the two groups. Stress, someone has suggested to me that, well, the animals were quite stressed in this study, being locked up in their cages and being tested upon, and that stress might be a negative factor in CR. Again, monkeys will be expected to be more susceptible to stress, of course, than mice will be. And also, another point that has been made is that the diet contained quite a lot of vitamin A, and that monkeys are quite susceptible to the side effects of this. Human studies, I'm not going to discuss them, but I'm just list them. There are several human studies, no studies, of course, on lifespan, only studies on the metabolic effects of CR, and they are looking promising in the metabolic effects. By the way, they are not all purely CR. The Minnesota experiment is clearly an alternative, not even an alternative fasting, it's more like starvation actually. It's quite severely restricted. I won't call that CR anymore. The test subjects were really on extreme CR, on starvation. The benefits of CR are cardiovascular disease risk factors are improved also in humans. Cancer risk is significantly reduced in virtually all studies. There are some studies showing reductions in amyloid beta and in tau pathology in transgenic models that have been put on CR. In humans, there was a study that showed that a short period of time of calorie restriction improved their memory score. There have been several studies, including in monkeys, that showed beneficial effects on sarcopenia, the prevention of sarcopenia, so that means loss of muscle tissue with age. There is very well established that CR protects against autoimmune disease, especially earlier on in last century, there, like the 1940s, 50s, 60s and so on, there were lots of studies on autoimmune disease models with CR that showed a huge improvement. And finally, there are some data that show that CR might protect against toxic effects of certain drugs, where the maximum tolerable dosages of the drugs was increased in the CR group, and also more recent fasting, that 2 days of fasting protected against doxorubicin, which is a drug for the treatment of cancer, that it protected against the cardiotoxic effects of that drug. There are also some risks, osteoporosis. Although in humans, in this CRS study, we don't see any decrease in the bone quality, but in general you see decreases in the bone mass, the bone mineral density, and all other factors of the bone. On the other hand, when you do CR, you are lighter, your body weight is lighter, so you would expect that the bone strength would have to be less in order to support your body mass. So it might just be a compensation there and not really a negative effect. Susceptibility to infections. There was a lot of literature, really a huge amount of literature, showing all kinds of beneficial effects on the immune system, but only 3 studies so far have been performed where the animals were infected with an infective agent, and then was looked what happens. Do they die more or do they die less? And sadly enough, in all 3 studies, there is more dying in the CR group. Fertility is decreased. However, when you stop with CR, it's even improved. And there was also a study showing that CR actually protects against, with age in the female, you have different changes in the egg cells that can increase the risk of an abortion, a natural spontaneous abortion of the fetus. And these defects were prevented by CR. So, although it reduces your fertility when you stop CR, the fertility is improved, and probably the risk of spontaneous abortion is also lower. Then amyotrophic lateral sclerosis. There are data showing that CR is bad. There are data showing that actually eating more might be beneficial in these patients. So that might be another disease where CR is negative. Wound healing might be impaired by CR. There isn't really much research at all on this. Although when you refeed the animals, wound healing is actually improved. And hunger, of course, hunger is an obvious, it's not really a risk. I mean, you can't consider that to be a risk medically seen, but it's certainly a negative effect. The mechanisms, I'm not going to talk about the mechanisms in any detail. I'm just showing that there are a huge list of proposed mechanisms so far. And I'm just going to later on discuss one of my hypotheses on this. But first I want to look a little bit at intermittent fasting and also at restriction of specific macronutrients. So intermittent fasting has been shown in many studies is to increase lifespan. However, what I really wanted to show you is that there are 2 recent studies that really say that alternative fasting is not the same as CR. and that alternative fasting might have negative health consequences. And in the second study, they actually showed that the negative consequences did not happen in the CR group, but did happen in the alternative fasting group. Restriction of specific macronutrients has also been shown to have positive effects. So the old idea that CR works in all animals, in all genotypes, and that the diet you give to the animals is not important at all, is essentially probably disproven. So the surprising data essentially is that, and that we discussed yesterday, and I think I will have to quickly reduce my time for the lecture. We had a lot of talk yesterday about the fat mass and the bariatric surgery that improved on a very short period of time insulin sensitivity without the effect of weight loss. And there was also this study that showed that animals who retained the most body fat on CR had the best, had a higher chance of having a lifespan extension. The ones who lost the most body fat had the highest chance of having their lifespan reduced by CR. So the question will be, what is going on? Is fat not important in insulin resistance and in diabetes? And what is fat necessary for CR? What is happening here? And so what I want to propose is that it's not really the amount of fat, but really the metabolic profile of the fat, so that you can just say the total amount of body fat is that person and look then to what the effects are, but that you really have to ask, what is the fat doing metabolically? So the metabolic reprogramming of the fat, and that can be influenced by, well, food intake, but many other factors, of course. So that will be calorie restriction will reprogram your fat tissue and will make your fat tissue secrete healthy factors, healthy adipokins, instead of the unhealthy ones that cause insulin resistance. And so they lead to improvements in heart health, in muscles, and in liver. So, well, here I'm going to quickly skip over, but I'm just saying that the profile of the secreted factors changes between the diets. Now, of course, this is a hypothesis. There will really have to be a study that investigates this in more details. I think Adiponectin is just one of these factors, but that might be really an important one. And it has been shown to have influence in CR, but I'm not going to talk about it. Yeah, it's related to CR pathways too, and to life expansion pathways. And then the last two slides, essentially, the question is, we can do CR in humans, people don't like it, so can we mimic it pharmacologically? Well, yes, there are a whole list of CR mimetics that are being researched. However, I will say I want to focus on metformin, because metformin is really the only one that is safe and has a good evidence for being a CR mimetic. So metformin increases the lifespan in several mice and rat strains, increases it in C. elegans. However, in Fisher 344 rats, they failed to find an extension of lifespan, and also in the male 129 SV mice. However, that study had a real big problem, and that was that in the CR group, glucose was increased by 1 millimolar, and that's really abnormal. So that's why I really had questions with that study. And then finally, the last thing that I wanted to show is that actually when you feed metformin to mice and you look at the gene expression changes, it mimics 75% of these changes in that 8 weeks time of the long-term effects of calorie restriction. When you put the animals on calorie restriction itself for 8 weeks, so short-term calorie restriction, it only mimics 71%. So it seems that metformin is even mimicking CR quicker than CR itself. And then I finish. Thank you very much.